Okay, so yeah, I'm Eric Kerfoot. I'm a software architect at the Biomedical Engineering and Imaging Sciences Department at King's College London. So what I'll be doing here is walking you through some introductory code with MONAI. So going over a little bit of the design, the architecture, and starting off with our transforms library. So for those who are in Colab, this is the command line to do the installation that you need on top of whatever is provided in Colab. And if you're running in other environments, this is pretty well what you should be running as well too. So even if you're under Anaconda, my experience is that this pip line will still work for that. You should create a new environment perhaps just to be sure, but this should work everywhere. Within Colab, also you should change your runtime to use GPUs. Otherwise, it'll just be in CPU mode. So this is the basic instructions for doing that. And then running NVIDIA SMI afterwards in a cell will just verify that we've done all that correctly. So as we said earlier, this notebook and the others for today are available already right now on the repo that has been linked in the Discord. So if you want to follow along and do it yourself, that's where to get it. There'll be links taking you directly to the Colab versions. And at the very end, we'll be doing a little bit of hands-on exercise for about 10 minutes or so. So if you want to do that live with us, then get ready now whilst I talk. So as Stephen has said, what MONAI is our PyTorch library for deep learning in healthcare. And this covers a lot of things that we want to do. You know, we want to have something that's going to be a community for collaboration between academics, industrial and clinical users. We want to have something that's going to be a state-of-the-art environment entirely for doing our training and eventually for doing our deployment as well. We'll be talking about that later on in this bootcamp. We want to be able to provide our optimized and standardized ways of creating and doing the evaluation of deep learning models. So there's a lot of components that need to go into doing that correctly. So looking at what is our basic outline of the training process, you know, we have our data come in as NIFTs, DICOMs, or other formats. We have to apply some transforms to regularize that data and apply data augmentation during training as well. We then are going to load this data through certain classes to do this in an optimal way during training. And then during the actual training and evaluation process, of course, we have our models that are composed of different networks, and those networks are composed of different blocks. We have our evaluation classes and definitions that are using certain descriptions of what metrics are, so mean dice, for example. We have our loss functions as well. And we also have utilities for visualization and for saving data and models out to files. So there's various components to that, but that's the basic overall workflow. So in MONAI, we want to be able to provide the components that will make this process faster and more efficient and more reproducible, and something that will save us from having to reinvent the wheel. So a generalizable, general purpose modular framework is what we're targeting. So why do we need this? You know, there's a number of things in biomedical applications that are very specific. You know, these are requirements that are very particular to the sorts of tasks that we would carry out in this area. Certainly loading data that has a certain format, so magnetic resonance or computed tomography, these formats are not just images, of course. We know that the values have specific meanings, specific physical meanings that differ depending upon what the acquisition modality was. The data formats this is stored in is quite often DICOM, but we see others like NIFTY, which is very common for us, and even just photographic formats as well. These things need to be understood and supported and interpreted in the correct way. In the case of DICOM, the actual ontology that represents can be quite complex, so we need to have specialized software to understand what that is. We know that certain network architectures, of course, are better suited for biomedical applications. You know, UNet is the classic example Steve mentioned already. And so we want to have also data transfers that will operate on this data and be able to regularize it for us in a certain way. So do the pre-processing for us, and then also do specialized augmentations that aren't just the sort of augmentations you would get when augmenting natural imaging. So being able to actually manipulate data in the MR space, for example, in ways that's understood to be meaningful for MR images. It might not be the same for other sorts of images or for natural images for that matter. We also want to have transforms for post-processing data so that we can manipulate outputs from networks and analyze that as well. So all this contributes to reproducible science in the sense that providing this toolkit then gives people that baseline of software that they can build their own models and experiments on. And so if more and more people are using the same base level of toolkit, then there's far less that others need to then understand and learn to be able to use your model that you've published, or be able to reproduce your experiments that you've put publicly on GitHub, for example. So this not only saves people time in having to re-implement the same thing over and over, it does provide that sort of basis for understanding. And this is the sort of things that we do want to provide with MONAI. So we want to have all of the utilities for doing our data loading and handling, the transforms, which we'll just talk about in a little while. These are things we want to use for processing, regularizing, and augmenting our data. And then, of course, contributing all the other components we want during our training process. So if we just have a look over the general architecture of MONAI and looking at what our components are. Of course, at the research level, we have our ability to provide our models, to be able to provide our examples and our experiments in sort of a ready-made package. So that's going to be at that level. We have examples for how to do various operations as well. So it's various experiments that people will quite commonly undertake, such as segmentation and classification. We want to provide a lot of ready-made examples that don't just demonstrate how to use MONAI, but are actually quite useful to take away and just adapt to your own purposes very readily without having to write a lot yourself. At the actual workflows level of MONAI, we are providing a lot of utilities on top of PyTorch Ignite, which is a high-level library defining the whole training and validation process in terms of modular, object-oriented class structures. So we want to extend and provide more utility on top of that, as well as the handlers to provide various utilities for us during the training process, such as loading or saving checkpoints, exporting data to TensorBoard, doing the actual evaluation of networks at during training time, sorting out the scheduling for a learning rate or for other utilities that require information at certain times during the training process. There's a lot of utilities that are provided through our handlers. Then we also have our metrics that we are using to analyze and interpret what the performance of our network is during training and afterwards. Finally, at the low level, we have various utilities for defining our networks as well. So we have our actual network definitions, but then also the individual blocks that compose those networks, and then the layers that compose those blocks. And these are designed in a modular fashion that should be reusable to others who are using PyTorch already. So there's no huge buy-in in terms of being able to use and mix and match our code with existing or new PyTorch code. We also have our transform libraries and our libraries of ready-made loss functions. We also have various data set definitions that inherit from the PyTorch data sets, but provide a lot of other extra utilities that make the training process more efficient and provide other functionality that would be important during the training process. So our MONAI design philosophy, we've touched on this earlier, but we want MONAI to look like PyTorch. So if you're familiar with PyTorch code already, MONAI should look very similar. And we don't want to be enforcing any sort of design philosophy additional to PyTorch. Anything we're doing is going to be additive on top of the PyTorch way of doing things. We want to adhere to the same design philosophy and require any sort of new things to be just additional on top of that. And modularity is very important so that our components that exist in MONAI can be used in isolation with existing code, and you don't need to buy into the entire MONAI way of doing things or are forced to inherit from the MONAI inheritance structure in any way. So you should be able to mix and match existing PyTorch code with MONAI code without much difficulty. And so this contributes to collaboration, because people's existing code they don't have to rewrite, and so they can integrate that. They can start to use pieces of MONAI without having to change over and use the whole library at once. So this is the idea about trying to be modular and trying to be friendly to existing ecosystems, so we can bring people on board rather than being competitive to what already exists. So with that out of the way, we can now actually get to the nuts and bolts of actually programming code with MONAI. So our transform library is quite extensive, and it's what we use for doing data regularization and for augmentation at training time. So first of all, we will just go through what array transforms are and then talk about what we can do with custom transforms and what needs to be done to actually write your own custom ones, and in what dictionary transforms are, and then looking at how we create our data sets and data loaders using transforms. So we start off with just some very basic importation here. So importing MONAI, we can pull into the individual components from various submodules that we'll just use here. And we have a print config function here, which is just a general purpose sanity check that we quite often use to make sure that we've actually imported things correctly with the right versions. In this case, so we have. So what we want to do with our transforms is define a data pipeline. We want to be able to put our raw data in whatever format that is, and get some usable data out that can then be fed directly into a network, and also have the information about comparing ground truths or other metadata that might be important during training time. So with our highly specialized medical imaging, there's various operations you'd want to perform. Certainly loading this data from different file formats has to be supported. So if our initial input data is file names, then we need to be able to turn that into actually loaded data. We then want to be able to apply augmentation. So in this case, we want to rotate images as in the middle examples here, as well as their segmentations, and then also apply more useful and more regularizing augmentations, such as non-rigid deformation, as demonstrated in the right-hand side. So we have various transforms in MONAI that will perform these operations for us, and the way that we can compose these together into a sequence of transforms and compose that again with our means for loading data and for caching data as well too. So we'll see that later on. So our transforms are designed to support both individual arrays as inputs, as well as dictionaries of arrays as inputs. So our transforms can accept one array and then perform some operation and return another array as its final result. We can also accept dictionaries and apply our transformations, whatever that is, to nominated members of that dictionary, and then return a new dictionary with the non-modified members also included. So this allows us to add data during the pipeline process if we actually wanted to, and that is something that'd be quite useful later on. And if anyone's used torch vision before, this should be a very familiar sort of architectural choice. This is something we deliberately chose to inherit from that library, the way of defining transforms and then a chain using a compose type. So we'll see how that looks later on. Looking at a few examples of our medical image specific transforms, we have load image, which is used for loading medical specific file formats, as well as some photographic formats. We have spacing for being able to resample images based upon the definition of pixdim, which is a value that you get from nifty images, for example. We can also adjust the orientation, once again, from nifty metadata using the access codes. And then we have adding random noise augmentations and normalizing our intensity. So this is about rescaling the values of an image to be a certain range. And we have affine transformations, and then our random deformation transforms as well. So what we'll do first of all is just generate some randomized data using some utilities from MONAI. So we will create a set of images and their segmentations using our random test image generation routine, which will create images with a bunch of spheres and then their segmentations to go along with that. So we'll create 5 of these and store these into Nifty files in a temporary directory. So that's pretty straightforward. And what we get then as our list of file names is going to be a list of dictionaries. So each dictionary is going to have an image and a seg field, and that's going to just map to the file name for those 2 Nifty files. So it's pretty straightforward. So looking at an example of using our array transforms directly, here in this case, we are using 3 different transforms: load image to convert a file name into an actual loaded image, which will also throw out any of the non-image data. So this will load a Nifty file and just store the actual imaging data itself. And so the header metadata will not be retained in this example. We then want to add a channel to this image, because typically what you'll get from Nifty files will be some image, certainly in this case, where the dimensions are just going to be height, width, and depth. And so we want to add a one size channel dimension to the beginning of that, because that's what PyTorch expects. It's channel first. And then we want to convert whatever that imaging data is to a tensor, because by default, everything uses NumPy arrays. And so we want to convert to tensor here so that it's something usable during the training process. Compose is our special transform, which takes a list of transforms and then passes the data through each in sequence, very much like torch vision's compose deliberately. So if we apply our input file name to this transform as if it were callable, we'll get our image array out. And we look at the properties of this. It is a tensor. Its shape is what we expect, as 256 cubed with our one size channel dimension added to it. And its device is -1, which means it lives on the CPU for now. So that would be something else if it was on device, of course. So that's a very simple pipeline for loading an image and just adding a channel to it. If we want to do something a little fancier with some custom code, it's actually very simple to do that with the transform called lambda, which will accept a callable, which will receive one array and then is expected to return an array. So we just modify our little pipeline here ever so slightly to replace the to tensor with our lambda instead. And the function we're going to pass in is something that will just sum along the dimension 1, which is, I believe, width, or maybe it's height. Anyway, it will sum in that dimension. And so what we'll get as output, it will be a 2-dimensional image. It will have a channel dimension. So we'll just look at the 0th channel for that and see what we get. So if you take a sphere and sum it in one dimension, you're just sort of taking it and flattening it out. And so you get just sort of the density of that sphere. And that's what that looks like here, with a number of spheres overlaid with one another. And that's the very simple way of doing that without any other sort of configuration values. This is quite often all you'd need to do a transform for a very simple operation. If we wanted to do things a little bit more complex, if we wanted to store some configuration values, or if we wanted to do anything else that might have some other data that needs to be retained, then what we will need to do is inherit from the transform class itself. So in this example, we're going to sum over whatever the dimension is we've actually specified. So by default, it'll be dimension 1, but we can specify whatever else we like. And so this will once again call sum on that array and do the summation in whatever dimension is being requested. So we can create this an instance of this class and pass in what our dim is going to be. So in this case, we'll sum over the height dimension instead. And if we pass in the same file into this transform pipeline instead, and then take a look at what our results, they're quite different. So we're now looking at it from the side rather than from the top, say. So this is quite often the sort of way to create your own transforms that you'll see in some of our example code, because when you do want to have configuration values like that, this is a cleaner way as opposed to using partial. So these transforms that we've used so far are what we term deterministic, in the sense that their output will always be the same for the given input. So if we want to have a transform that's going to be randomizable, something that's going to give random results, even if the same data is applied each and every time, and a transform that might not actually be applied at all, it might just be a no-op if it is randomly chosen, then we need to define a transform that inherits from the randomizable class as well. What this class is used to do is retain a random state object, as well as to clue in other code elsewhere that this is a non-deterministic transform. So there's other code that will check to see that if it inherits from randomizable, and if it does, we'll treat that transform slightly differently. Randomizable also comes with a set random state method, which is used to set the seed or to actually change the random state object that it has internally. We also have a randomized method, which is used to actually generate the random data, and will use a certain the probability values that will be passed into it to determine when to do this and what sort of randomized operation is going to actually perform. So our example here is going to randomly add additive noise to our image. So it's not going to do anything terribly fancy. It's just going to do a random uniform noise field and then add that to whatever our input image was. So what we are going to pass in as arguments to this class are going to be the probability of actually applying this transform, and the maximal value to actually add if we do. So the prob value we actually check at some point here on line 10 to see if we actually want to apply this transform or not. And so if we don't actually apply that, if the value is greater than whatever our prob is, then the noise we're going to add to our transform is going, or to our image is going to be 0. So it's just going to be the value 0, which is going to equate to essentially no op. And then we have an add noise method, which will just add whatever our noise field is to the image itself. And then whenever we call this actual transform, what's going to happen is the randomize method will be called, which will make that determination about whether to actually be a no op or not, and then to actually compute what our field is going to be. And then we'll actually perform the operation of adding the noise to our image. So if we run this with the default values, it will add noise to our image, as you see here, but we'll only do it half the time. And so this is something that's very important for during online training, where you don't necessarily want to apply a transform every time you query an image from your data set. You might want to apply it sometimes, you might want to apply it under certain conditions. And so this is their mechanism that's pretty straightforward to do that, to define something that's going to be randomly deterministic about whether to be applied or not. And then again, the actual randomized field itself, its state and how it's actually randomized is dependent upon this random state object that's included with the randomizable class. So that's something that you can then, of course, change and set to be something different if you want to control the actual random distribution of that field. So what we've seen so far has been transforms that take a single array as input and produce a single array as output. But as I said earlier, we can also define dictionary transforms. And what these expect is going to be arrays that where some keys will map to images and some keys might map to other data or metadata that you don't necessarily want to use. And will then apply operations to only certain members of that dictionary and then return a new dictionary with those members substituted with whatever has been augmented. So in our example here, what we're going to do is just call load image D directly, and the D suffix indicates this is a dictionary transform. And what we want to do is apply this load image operation only to the keys that we nominate. So FN keys is just going to be the pair image and seg. And so we want to apply whatever this operation is to whatever those two keys map to. So in this case, it's going to go to image, and we happen to know that for the input from file name 0 is going to be a dictionary mapping those keys to file names, which is exactly what we want. If we apply our transform to that dictionary of file names and then look at what we get out, we have our image and seg keys, which will map to the actual image data themselves. And then we also have these metadata dictionaries, which contain the headers from the two nifty files. So if you need that information in the future, this is one way of transporting that information along with the image data itself. If we want to define our own custom transforms, again, we have lambda D, which is our dictionary equivalent. And this is something that's designed to take will accept keys, but will still operate over the functions as if they were accepting only single arrays. And so you nominate which image you want or which members you want to apply the lambda to, and then that will get applied passing in the actual image data themselves. And then we can do the operations we did previously where we can summon one dimension or take, in this case, the max in another dimension. And so if we do that twice, what we'll get is operation that will change one member of our dictionary, and then another operation, a second one down here, that will change a different member again. And so you can chain the two lambdas together to do two different operations on two different parts of your data set as you pass them through. So our whole compose sequence, what it will do is load data from our two keys, add channels to both as well, and then do some width over the image and then max width over the segmentation. And so if we apply that transform, we'll get a dictionary back. We can pull those members out and then take a look at that two pair. And so as you see, they look very different from what we saw before. We've taken the summation on the left, we've taken the max on the right, which is just looks like segmentations have been overlaid on one another. So that's a very straightforward way of doing a more complex data pipeline with our dictionaries. And once again, if we want to define our own randomized dictionary transforms, then we want to inherit from randomizable again. But because it's a dictionary transform, we want to inherit from map transform, because this is going to be transforms over essentially mappings from keys to data values. So there's a little bit more extra complexity we want to add to this. But our example here, we can actually use the non-dictionary version of our transform that we defined above, and then apply this to a number of data values. And we can also set what our random state is for this using the same methods we used previously. So set random state, we just call the same method of our transform and also of the one that we inherit. So then we can set our state appropriately for both what we have and for who we are ourselves. And then randomize is just going to call the same method again on the internal transform instance that we have. So during call, as I said earlier, what we want our dictionary transforms to do is create a new dictionary that's going to have the keys that have been modified associated with the new data, as well as keys we didn't modify, just passed along as normal. So the way we can do this clearly is just to create a copy of the original dictionary we're passing in. And then for every key in self.keys, which will be the sequence of keys that we passed in that we wanted to apply to, for each of those, we just substitute what the value is in our new dictionary with our transformed equivalent. So in this case, you're going to add noise only to those nominated keys. So we can put that together and take a look at what we got. Using compose, once again, we want to load our two images, add our channels to our two images, and then we want to apply the additive noise only to our image, because this really makes sense to add noise to a segmentation in this sense. I suppose there's other instances where that would be a sensible way to do things, but in this case, normally what we want to do is just make the images harder to understand so that the network is forced to learn a harder problem. And so our ground truth should stay unchanged. Taking a look at what our images are, this is what we get, which is more or less what we expect. So looking at the methods we overrode here, set random state, as I stated, is used to set the random state object itself from NumPy or set the seed. And we need to do this not only for the receiver transform, but also for any internal transforms that it also uses. Randomize delegates that randomization to our internal transform that we have, and our call does our operation of creating a new dictionary and substituting the nominated members for their transformed versions. So we have our transforms. Now we want to create our data sets from these. We have in MONAI our own data set class, which inherits from that in PyTorch and adds a few extra little features, mostly about changing what the arguments are for the constructor. But if you're familiar with PyTorch's data set classes, then this will be very familiar as well. This will work very much the same. With the added change that we pass in our transform sequences along with the actual data itself. And so whenever a member is requested from our data set, it will be queried from whatever the original data is, and then the transform will be applied to it before being returned. So whenever we use a square bracket syntax, as we do here on line 5, this will query whatever our value is and then apply our transform sequence to that. And this will work for both array-based transforms and dictionary-based transforms, because in which case we're assuming that our sequence we're passing in is going to be a sequence of dictionaries itself. So taking a look at this, we get exactly what we expect out for this sequence of transforms. We've added our channel, and it is a tensor, and our device is -1, which is to say CPU. So we can apply this to create a supervised training set using the array data set, which essentially just combines two data sets together. We have two different data sequences, and we have two different transform sequences. So whenever we query a value from our data set, in this case, it's going to pull out a value from this set of data and then apply this set of transforms, and then also pull a value from this set of data and apply this set of transforms to it. And so looking at what we get from this, where we want to add our channel, add our additive noise to the image alone, and just do a random spatial crop on both. This is the operation that you get. And the important thing to notice is that array data set will make sure that the random state is coordinated between the two sequences. Because normally rand spatial crop is something that will just take a random cropping somewhere in the image and produce that as its result. But we want the same randomized spatial cropping to be chosen from both the image and the segmentation. And so if we apply the two different transforms to data, we have to reset whatever the random state is before doing that. Otherwise, both of these transform chains will be starting from an initial state that's different, but we want them to start from the same initial state so that the results are the same. So that will do that for you, and that will solve one major problem with trying to use two different transform chains at once. So another way that you can do the same thing is, again, to use our dictionary transforms instead. So if we want to actually go ahead and use our dictionary to do the same sort of operation as we did above, we want to apply our random noise to the image alone. And then random spatial crop will inherently apply the same cropping to each of the nominated images. So it won't just choose a random crop location from each image, it will choose the same one from each one. Of course, that assumes that they're all the same size, but that typically is true. So that will work out for us. So this will do the same operation in a little bit less code. And this makes sense if you have more than just two images. The array data set makes sense for simple supervised problems. And this is something that is a bit more flexible for other sorts of problems. So looking at output from that, this is produced exactly what we expected. So again, if we want to then take our data set and use this with PyTorch's data loader class, which is what's actually used to load data during training time, we can just pass that straight in because it is, as I said earlier, inheriting from PyTorch's data set. And our own version of data loader in MONAI inherits from PyTorch's and adds just a little bit of changes to the constructor, and that really is it. So passing our data loader, this is an iterable class, and so we can use our little first function to pull out the first value from that and take a look at what we got. And of course, this is our dictionary at output because we're passing in a dictionary data set. Looking at what the keys are, we have our image and our seg, and then the metadata that goes with that. And we also have other information that's been passed along as part of the transform so that they can keep track of what operations have been applied to the images and to the seg, which would be useful later on for doing inverse transforms. We can also take a look at the shape of the image, and this is more or less what we expect. It's going to have a batch dimension, channel dimension, and then our spatial dimensions. And it's 128 as we expected. And taking a look at some examples, this is what we expect. We have added noise to some of our images and not to others, but we've cropped all of them in exactly the same way so that the segmentations line up with the images. So that's been the whirlwind tour of our transforms in MONAI. So now we're going to move on to the actual hands-on assignments. We have two here, and we may not have time to get through both of them, but we'll see what we can do. There's a bit of description of what we want to do. Here we want to define our own random flipping transform. And in the next one, we want to actually create our data set and our data loaders and see what we get out of them in terms of getting data that adheres to our specifications. So I will give everyone a bit of time. I'm not sure, Michael, how much time do we have left?
Yeah, so let's give people about 5 to 10 minutes. I think my section I can go through a little faster. So let's try for 5 minutes, see where people are at, and then we can come back and maybe start reviewing.
Okay. And I'll attempt to monitor the various chat channels to see if anyone has any questions.
Yeah, definitely. So again, so feel free to do the assignments. If you're using Google Colab, you can do it on there or on your own machine. If you don't have a machine to work on or you don't want to try working on it, we will go over the solution for it, and the solutions will be posted afterward as well. So if you feel like it, do it now. If not, then you can always try it at a later day as well. And we'll review it here in about 5 minutes.
Okay. So I'll just very briefly go through the solutions to our two problems for now, and then I will pass it on to Michael.
Cool.
So looking at the rand flipped rect example here, the definition that we wanted to have here is to choose some rectangle, or in this case, really a subcube of the whole image, and then transpose it in one dimension that we chose, or maybe multiple dimensions. So my example here, we have some probability of whether to apply it or not. And then what this will do is actually modify the data that's being passed into a rand flip function here that does the actual operation. So this will determine whether to apply the operation or not. We'll then choose a position to start from. So this will, XYZ will be our minimal coordinate somewhere in this volume. And then we make a number of choices. So there's a 33% probability of transposing our patch that we've selected in one of the three spatial dimensions. So this assumes that there's 3 spatial dimensions. So it's a little bit hard coded about being 3-dimensional. A more generalized version would actually check to see how many dimensions you have. But this will do for us right now. Having done that, we then just splat our patch back into the original data, and then that's what will get ultimately returned. So I hope that makes sense to everyone. This is a little bit more involved than the examples we saw in the slides, but this is the sort of operation you can think about it as being a random augmentation to the data that you need to do at some point in time to figure out like where you are in this image. So I don't know about, sorry, I'm just going to move on to the assignment 2. We are running short of time here. Yeah. So what we wanted to do was get a sequence of transforms that are going to, at our channel dimension, crop our images down to 200 cubed, rescale the values for the image to 0 to 1, and ensure that the data types for our 2 images, or for our image segmentation, were floats and integers. So we wanted to import a number of our transforms to do that for us. So we've already seen load image and add channel D. Center spatial crop D is going to do our cropping for us. If we say just a number, in this case, it'll apply that size to every spatial dimension it encounters. So in our case, it'll be 3. So that'll give us a 200 cubed volume. We then scale the intensity of the image only. And by default, that the range will be 0 to 1. And so those values didn't have to be provided here. And then cast to type D will then cast whatever the named keys are here to these types in those order. So the first one will be float 32 and the second will be int 32. And that's what we actually want to get out of the sequence, and just see what that result actually is. So for us, this will give us the results we actually expect. And if we look at the unique values for segmentation, they are all integer as we expected. And looking at what that is, that looks like that. Now with our data set and our data loader, just passing in our file names as we did before into our data set, and our transform sequence just here is the transform argument is all we need to do. And then the data loader itself, again, we just pass in our data set and then specify our batch size, and number of workers is, I think, just gonna be 1. So then we iterate over those, over every batch that we have there, which is going to be 3 batches, I believe. No, we're going only 2 batches, sorry. Yeah, 2 batches, one that's going to have 3 images, and another one that's going to have 2 only, because we only have 5 to choose from. So that's all there is for that example. So I think I'm done for that, and I'm going to pass it along.